Have you ever looked up at a massive concrete bridge and wondered, how exactly does it hold together under all those immense loads without just cracking right down the middle? Well, today we're diving deep into the fascinating mechanics of pre-stressed concrete sections for Flexure. In this explainer, we're going to unpack Professor Arvind Deshmukh's lecture on the Indian Standard Code IS 1343, and we're going to translate those complex engineering principles into a crystal clear understanding. Here is our roadmap for today's explainer. 1. The core flexure principle. 2. Real-world flanged sections. 3. Bonded versus unbonded tendons. 4. The eye girder design challenge. 5. The 11-step design playbook. And finally, 6. The true engineer's mark. We'll be taking a journey from the fundamental theoretical equations all the way to a practical, real-world calculation where things, as you'll see very shortly, don't quite go as expected. All right, Section 1, the core flexure principle. Let's start by laying our foundation with a quick recap. This essential equation right here is the absolute bedrock upon which all our complex calculations are going to be built today. The ultimate design moment, MU, absolutely must be less than or equal to the ultimate moment of resistance of the section, MR. And how do we find that resistance? We use the stress block concept. At failure, the concrete compressive stress is taken as 0.45 times the concrete's characteristic strength, acting over a specific depth of 0.42 times the neutral axis depth. If you just keep this balance of forces in mind, the rest of the puzzle pieces will fall right into place. Moving on to Section 2, real-world flanged sections. Rectangular beams are fine for textbook theory, but let's step out onto a real Indian bridge construction site. In the real world, especially for massive bridges and flyovers, we rarely use simple rectangular beams. They're just too heavy and incredibly inefficient for long spans. Instead, we use flanged sections, like eye girders or T-beams. Why? Well, in a beam experiencing downward or sagging bending, the top flange handles the heavy compression. Meanwhile, the bottom flange and the thin vertical web efficiently manage the tension through pre-stressing steel. Basically, those flanges give us a nice, large area to handle the compression without adding a ton of useless dead weight right in the middle of the beam. Now, when we analyze these flange sections, we hit a crucial fork in the road, and it depends entirely on where the neutral axis lands. Take a look at scenario A. If the neutral axis lies within the top flange, the entire compression zone is inside that flange. Easy, right? We can essentially treat it like a simple rectangular section. But look at scenario B. If that neutral axis drops down into the web, the compression zone suddenly includes both the flange and part of the web. At that point, those simple rectangular formulas completely collapse, and we have to rely on some much more complex strain compatibility methods to sum the compression from both of those areas. Which brings us to Section 3, bonded versus unbonded tendons. Before we calculate anything, we have to understand a critical distinction in Indian design practice. We have bonded tendons and we have unbonded tendons. With bonded tendons, the steel is grouted directly to the concrete. That means at ultimate load, the strain in the steel is directly compatible with the concrete right next to it. For this, the IS 1343 code tells us to use Table 11. On the flip side, unbonded tendons are free to move within a duct. Now, you see this in slabs sometimes, but it's not great for heavy bridge infrastructure. Because Indian bridges demand incredibly high durability, we focus almost exclusively on bonded grouted tendons. So Table 11 is going to be our best friend today. All right, Section 4, the eye girder design challenge. Buckle up, because this is where our design gets very real. We're tasked with checking the ultimate strength of a massive eye girder for a bridge. It has an effective span of 24 meters, uses high-strength M50 concrete, and utilizes those bonded 7-wire strands we were just talking about. The top flange is 600 millimeters wide and 150 millimeters thick. After calculating our dead loads and live loads, we're looking at an ultimate design moment, our MU, of a massive 3,996 kilonewton meters. So, to check if our section can handle this massive moment, we have to calculate the effective reinforcement ratio. But we immediately hit a roadblock. The formula requires us to input the width of the concrete section, but remember that fork in the road we discussed earlier? We don't know if the neutral axis is up in the 600 millimeter flange or down in the 200 millimeter web yet. So, which width do we even plug into our formula? Well, as any good structural detective would do, we just make an educated initial assumption to get moving. We're going to assume that the neutral axis safely falls within that top flange. Therefore, we'll just use the full flange width of 600 millimeters for our calculation right now, fully planning to iterate and adapt if the math proves us wrong later. So we plug that 600 millimeter width into our ratio formula. We take that ratio straight to Table 11 of the IS 1343 code for bonded tendons, and we calculate our neutral axis depth, XU. The math tells us XU is exactly 528 millimeters from the top. And here is our plot twist. Our calculated neutral axis depth is 528 millimeters. But remember our girder dimensions? Our flange thickness is only 150 millimeters. 528 is much, much larger than 150. Our assumption was completely wrong. The neutral axis doesn't sit neatly in the top flange. It actually falls deep down into the web. Because of this, the standard, simple, rectangular formulas collapse. We are officially forced into scenario B, performing a true, complex, flanged section analysis. Because that neutral axis is in the web, we have to calculate the compression from the flange and add it to the compression from the web. In Professor Deschmach's example, this yields a total compressive force of 1.67 meganewtons. But wait, the tensile force in our steel is 6.58 meganewtons. They are totally unbalanced. This means our assumed neutral axis was way too small, and we have to iterate. We have to essentially guess, check, and adjust the area of steel and the neutral axis depth over and over again. It's a really intense, iterative process of balancing total compression against tensile force until perfect equilibrium is achieved. Let's move to Section 5, the 11-step design playbook, to make sure you never get lost in these calculations. The IS 1343 outlines a rigorous 11-step procedure for this exact process. But honestly, it really boils down to these 4 critical phases. First, you handle your loads and dimensions. Second, you calculate your moment and that tricky reinforcement ratio. Third, you hit Table 11 to check where your neutral axis actually is, and of course, prepare for a plot twist. Finally, you calculate your ultimate resistance and run your safety checks for shear and deflection. And the summary right here brilliantly captures the non-negotiable codal provisions you absolutely must adhere to while following those steps. For instance, the code caps the maximum reinforcement ratio so that the failure of the beam is ductile, meaning it bends noticeably, rather than just snapping suddenly and catastrophically. It also mandates a minimum amount of steel to prevent brittle failure. Guys, these aren't just suggestions, they are the literal guardrails keeping the public safe when they drive over these bridges every day. Finally, Section 6, the true engineer's mark. Let's talk about the elephant in the room. Why do we do this? A very fair question to ask is, why go through all this grueling, iterative, manual math when modern software can literally do it in 2 seconds? Well, at the end of his lecture, Professor Deschmach leaves his class with a challenging homework assignment. He asked them to manually find the perfectly balanced area of steel for this exact eye section, making them prove they actually grasp the underlying physical mechanics before they are ever allowed to touch a computer. He reminds his students that software like STAAD or ETABS will absolutely solve these iterations instantly, but the software can't think. It doesn't know if your assumed flange width is actually practical to build on a messy construction site. It doesn't know if the specific steel strand diameter you selected is actually available to buy in the local market. True engineering doesn't happen in the processor of a computer, it happens in the mind of the engineer. So, as we wrap up this explainer, I want to leave you with this thought. When you are out there designing the infrastructure of tomorrow, are you just going to rely on automated software to do all the heavy lifting? Or are you ready to become a true engineer who can literally feel the forces in the structure? Keep pushing your understanding to the ultimate limit, and I'll see you in the next one.